Have you ever thought about this head-scratching paradox? You've got a spoon, a kitchen sink, or even a whole refrigerator made of stainless steel. It's got steel in the name, so you expect a magnet to stick, but nothing happens. It's super weird, right? Because stainless steel is made mostly of iron, typically over 50%, which is the ultimate magnetic metal. It also contains a good amount of nickel, which is also strongly magnetic. So how can a combination of these two elements be non-magnetic?
The answer isn't about what's in stainless steel, but how its atoms are arranged. In this video, I'm going to solve this scientific mystery, and I promise you, you'll never look at your kitchen appliances the same way again.
Before we jump in, if you love to understand the hidden secrets of the world around you, please go ahead and hit that like button, subscribe to the channel, and turn on notifications so you don't miss our next video. To understand stainless steel, let's take a quick look at how magnetism works on a tiny atomic level. The magnetism in metals comes from a quantum property of electrons called spin. Every single electron is a tiny spinning magnet. In most materials, these little magnets are paired up in opposite directions, and their magnetic effects cancel each other out, which is why most things aren't magnetic. But in ferromagnetic materials like iron, something special happens. The tiny magnets inside groups of atoms spontaneously align in the same direction, forming highly magnetic regions called magnetic domains. In an unmagnetized piece of metal, these domains are all jumbled up, so there's no net magnetic force. But when you introduce an external magnet, these domains snap into alignment, creating a powerful attraction. So the real question isn't, does the material have iron, but rather, does its internal structure allow those iron atoms to align and organize in this way? This is where the true secret lies. It all comes down to the metal's crystal lattice structure, the precise way its atoms are stacked together like bricks in a building. The magnetic family. These steels have a structure called a body-centered cubic lattice. Think of a cube with an atom at each corner and one single atom right in the center. This specific arrangement facilitates the long-range alignment of electron spins in the iron atoms, which is a prerequisite for ferromagnetism. That's why grades like ferritic and martensitic stainless steels are strongly magnetic. The non-magnetic family. This is the Austenitic family. These steels have a completely different structure called a face-centered cubic lattice. In this arrangement, you still have atoms at each corner, but instead of one in the middle, you have an atom at the center of each of the 6 faces of the cube. This specific atomic spacing and arrangement fundamentally disrupts the alignment of those magnetic domains we talked about. This is why austenitic grades like type 304 and 316 are considered non-magnetic in their pure form. So austenitic stainless steel isn't non-magnetic because it lacks iron. It's because its crystal structure actively prevents the iron's magnetism from manifesting on a larger scale.
You might be thinking, wait a minute, what about the nickel? It's a ferromagnetic metal. Why would you add it to a steel to make it less magnetic? This is the most counterintuitive part of the whole story. Nickel's job isn't to add magnetism, its primary role is to be a powerful austenite stabilizer. It's the key ingredient that forces the steel to maintain its non-magnetic FCC structure at room temperature, even when it wants to transform into a magnetic phase. In a sense, nickel is the architect. It ensures the house of the crystal lattice is built in a way that makes it impossible for magnetism to live inside.
Now, for one last twist, have you ever noticed that a stainless steel pan or a spoon might be non-magnetic, but a small part of it, like a wire or a bend, is slightly magnetic? This is due to a phenomenon called strain-induced martensitic transformation. When you mechanically deform stainless steel through cold working, like bending, stamping, or drawing, you introduce enough stress into the material to force a small portion of the non-magnetic ferromagnetic austenite, or FCC structure, to change into a magnetic martensite, or BCT phase. This is why a soft, ductile stainless steel cotter pin isn't magnetic, but a springy stainless steel spring of the same grade is. The magnetism isn't a flaw, it's a direct result of the manufacturing process that gave the metal its final shape and strength. The same thing can happen during welding, where a small amount of a magnetic phase is intentionally added to the weld to prevent cracking.
So, the story of magnetism in stainless steel isn't a simple yes or no. It's a complex, fascinating interaction between chemistry, metallurgy, and atomic architecture. The presence of iron is a starting point, but the final outcome is all about how those atoms are arranged. But now, for the most exciting question, can you reverse this? If stainless steel becomes magnetic from cold working or welding, can we use heat to turn it back into its original non-magnetic state? The answer is yes, you can, and the process is called solution annealing. Join us next time to learn how this incredible heat treatment works. Don't miss out on that video. Make sure you're subscribed and have the notification bell turned on. Share this video with a friend who loves a good science puzzle. Thanks for watching, and we'll see you soon.